Okay, folks, welcome to Lecture 8 on computer graphics here. Let's go ahead and dive into our pre-class warm-up, and then I'll talk a little bit more about the logistics coming up. And for today's warm-up, I want to show you something cool in computer graphics, which is the one equation to rule them all, or so they sort of say. There's something in computer graphics called the rendering equation, and it's essentially a big algorithm that presents some partial solution to create a photorealistic effect. That is this equation here. If we do some of the math here, describes how to create a sort of pixel perfect image. Okay, so here's sort of the one equation to rule them all reference, but it's actually not, it looks kind of scary, you see an integral here, but really it's just a function here that takes some parameters here describing how light interacts with the geometry of your scene and how to accumulate a particular color there. Okay, so there's actually a nice video here which breaks down the rendering equation into smaller steps that you can follow along if you're interested. And we're going to actually work on implementing part of this equation to do lighting in our computer graphics scenes. Okay, so we are live and recording, so some logistics, as mentioned. Assignment 4 has been released. We'll be adding textures to our model loader, so many folks have already started with that. You have another few days to keep working on it, so please get a head start. Lab 8 has been pushed to your repo, so please do a pull for that. And final project repositories are out. Okay, so let me just give a sort of view on where we are in the semester. So we are on week 8, if you can believe it or not, and we have a few more weeks to go. But I'd like folks to start thinking about their final projects sooner than later. So I've attached a few links here. I will dive into these slideshows in a moment, but just looking at it, we have we're at week 9, 10, 11, 12, 13, 14, and then the final week you'll have your, we won't do presentations since we're not here, but the final project submission, and it's going to come up faster than you might expect. So what I will suggest doing, and actually let me just dive into this now, is looking at some of the final project ideas. So I'll sort of just talk over this, that you have a range of things that you can work on in this class. You can work on really anything you'd like that's computer graphics related. Granted, it's in a low-level graphics API like OpenGL that we've been using. You could use DirectX or something else, or Vulkan, Metal, these other APIs if you'd like. And then something graphics related. So here's sort of a train rendering demo, a cool city rendering. I'll click on a few of these actually. You'll have to watch them on your own time. Oops. Let's see if we can skip these ads, but some of these are just really cool and worth sort of watching. And you certainly, the ones I'm posting here are ones that you have the skill set, or at least by the last few weeks to start implementing these. Okay, so I want you to just sort of look at these, start getting inspired. Here's one on rendering terrain, this idea of having different levels of detail. So stuff that's further away renders with fewer triangles, stuff that's closer has more triangles. We are going to get into this idea of ray tracing later on in the scene, which is another way of rendering. So here's 2 examples of that, and you can see this one's working in real time with some lighting effects, which is pretty cool. Radiosity is another form of this idea of ray tracing, just another way to sort of light your scenes up in a photorealistic way. Constructive solid geometry is a way to sort of, here's a drill bit, but drill and carve and change geometry. Let's go ahead and try this link as well. So you can see this drill sort of going through and removing some geometry. Progressive meshing is one of my favorites. So again, with that idea of levels of detail, here's the bunny model, and then here's a lower resolution version of it on the left, where you've algorithmically removed some triangles to have a less geometry version of that model rendering. And this can be for improving performance. So here you can get an idea of how it works. You have a high resolution model. As we lower the slider, we have less triangles that we render, and you can even see the program starts running faster. It's spinning faster as there's less detail to draw. So that's a fun one. Subdivision surfaces is another idea of that, just tessellating or adding more triangles into your scene. This gives you more normals, smoother geometry. Same idea here. This is a very popular technique you'll see used in Pixar films. They're known for having lots of good subdivision surface algorithms. Decimation of meshes, again, it's that same idea of a high resolution model, and then here's that same model at 0.1% detail. But it still preserves nicely the rough form of this figurine here, so you can still tell it's some character. Deformable components, again, sort of a physics simulation here. Let's go ahead and run this as a quick clip here. You can see how the mesh deforms here in different ways. By mesh, I just mean the cube here. In fact, it's got a sort of material to it, so depending on maybe how heavy the sphere is. Volume rendering is a technique often used for rendering medical data. So if you've ever gotten an MRI or X-ray or these kind of things, you can visualize in 3D your bones and stuff to see what's going on, and you can sort of slice through and see what the actual interior looks like. So you'll see this idea of slicing where you're kind of looking through the image here in different ways. It's pretty cool. So that's volume rendering. Animation could be various forms of actual character animation. This is sort of a flocking behavior, so it's sort of a mix of artificial intelligence, a very simple sort of agent here, these birds flocking to the ball here, and then sort of moving around. So this is sort of a AI application of animation. There could be other animation more in the physics sense, if you like. This sort of pendulum demo here, where you can see the links here on the pendulum or this chain here react to this figure moving. Okay. And this goes with various collision demos you could have. This is doing a sort of an algorithm known as sliding collision. So as you control this character here, this cube, and you can see which direction it's facing, it slides nicely against these figures. Okay. So more on the math side. And then various particle simulations that you could create here. Okay. Folks could make a small or simple game here where you load some models and move them around and maybe have some rules for racing. I think those would be a good candidate for a final project. You could work on different shaders as projects. So here's something called cell shading. It's a common technique used in games to give sort of a outline of characters, a hard outline here. That's why you see the dark towards the edges of figures, and it sort of gives this nice cartoonish effect. And then we can get more into different styles of rendering. So if you're interested in efficiency and sort of rendering cool I don't know, gaming scenes, you can see the difference here in the different textures that are applied. So this is something called deferred rendering, and you can see in each of these four areas here, position, albedo, normal, and shaded, these are the different textures that have applied. So this is just looking at position and coloring stuff. Here's your actual texture map, so something like we worked with the cat image from your previous lab and will continue today. Here's something called the normal, which is highlighting the normal maps. We'll get into that. And then this top quarter of the image is everything put together. So you can see just the different stages. And this idea is it's a deferred render because it's calculating all of these things and then deferring to render, once it has all this information, a final, nicely lit scene here. So you can see just a quarter of this scene here. Let me show you what it actually looks like. This is the actual scene, and you can watch the video just to see how they sort of nicely broke it down with different the stages. They're using something called the depth map which we've talked about with the Z buffer and so on. And there are some resources for these things, which I'll just quickly highlight. So for example, for the deferred shading, Learn OpenGL can have some guide and some help for these things. Okay, so those are some of the final project ideas. What I'm excited to do is to challenge you a little bit and see what all of my previous Northeastern graphics students have done. So I'm just going to quickly scroll through this. I'd like you to take a look at this on your own time, but I'm also going to give it a challenge that every year the projects have gotten better. So my expectations are high. You can see some of these previous projects. These are from all the students in no particular order, from different courses, and every semester I've gotten more and more impressed. So the bar is really high for you guys, which is I have high expectations, but I know this group can do it here. So here's from the last summer, which I thought did some really cool projects. And you can click on all these links to see the projects. This one came out particularly nice. Some of these ray tracer ones were quite nice. This is probably a favorite one, this grass shader here, and applied to the bunny, so you can see that. Another nice one here by some folks that actually went on to work for graphics companies later on. And here's another grass rendering that was popular. This one doesn't have a image. And some folks worked on implementing Minecraft, which is pretty cool. Okay, so for you guys, it's to be determined. Again, the bar is very, very high for final projects. Okay, so I want you to take some time to think about your final project. Look at the other ones, look at previous projects, just to see what I expect in a few weeks' time. And then you can start forming teams here in this spreadsheet if you need. 2 people to a team. So let me make a brief correction here. We're going to do teams of 2 since we're online, just to make things. And once you've formed your team, and mind you do not need to form a team for this project. Then you can click on the final project repository. I'm going to create instructors team, do not join for me. And then it'll create the repository for you. Okay, and then what this repository will look like, it'll have instructions for putting your team members here. I would like you, to read over this. You can see the rubrics. And one of the main deliverables of your project, as you'll note here, is going to be to put a few screenshots of your project that really showcase and show off what it's doing, and then also to make a YouTube video of your project running. So you can read about that in sort of the write-up here. I've got some strategy, how you'll build your project. You're going to just use the same build.py that we've been using or something equivalent. It makes it really easy for myself and the course staff to run your project, and then a video deliverable. So you can look at those other videos to get an idea. Here's one I particularly liked, and why I liked it. So you can spend time, watching that later on once you've thought about your project. Okay, so this is the repository you'll have, and then you can begin the project at any time that you like. Okay, so that's what I'll say about final projects for now. And let's go ahead and continue with our lecture otherwise. Okay, so last lecture we talked about textures and this idea of surface parameterization. That is, how do I take a 3D shape here with X, Y, and Z and wrap a 2D image around it. This is the term for UV mapping. And there's some larger problems with this, with how do you avoid distortion, and artists sort of have to manually do this process, and how to get through that. I talked about MIP mapping, which is a technique used, or rather implemented in OpenGL, for increasing the visual quality of a scene. This idea that you show more detail the closer up you are to the screen, and the further away you are, you can get away with showing less detail, but that's also how we sort of perceive things. and it avoids us from having a very grainy sort of looking texture. Okay. And then our practice was, we've used the ppm image format to look at different pixel colors. You were able to add a sampler 2D to your fragment shader and render this CAD image, or two of them rotating was one of the goals. 2 or 1 is fine. And then we got a little introduction to normal maps, this idea that textures, whether they contain a CAD on them or not, really are just 2D arrays of data. Sometimes they contain color information, but we can also encode other information on them. Okay, so for today, I want to take us to Hollywood, or in a sense, and just talk about lights, camera, and getting some more interesting action in our scenes here. Okay, so our goal for today is going to be to implement a camera class. One of our goals. We're going to have 2, cameras and lights. And this is going to allow us to move around our scenes in a much more nice way and push us more towards having an interactive graphical scene. Okay, so on camera, we've talked about this from our previous lectures, this idea of the model view projection matrix that is sort of working through where we have our model here when we load our shape, and then we apply some transformations to it. And then we have our camera, which sort of puts things in the right perspective, and then OpenGL sort of takes care of some of this other stuff with the GL viewport commands to clip stuff that's not visible after we're in our perspective mode, and then fit things to our window coordinates or the screen space. Okay, so here's just another picture. This is a nice diagram I borrowed from one of the OpenGL tutorials, but here it is left to right, actually a nicer way to look at it. Okay, so let's walk through this one more time here. And so I just want to walk through each of these steps of going from the model to world matrix, or local space to the world space. Okay, so just as a recap, the model matrix is taking some geometry, so we load up this model here and saying, hey, vertices, I want you to be positioned here in our giant 3D world. Okay, and I am taking you from your local coordinate space and positioning you somewhere in the world. Okay, so when we load up your model. Okay, and we've been doing this with our model transform matrix and the transform.h file, where you translate, rotate, and scale each vertex one at a time in the vertex shader when you first load a model or create some geometry. Okay, so here's the example from the actual transform.cpp, where you create a sort of identity matrix, everything's sort of centered in the origin of the world, and then if you'd like, you can use these sort of translate commands to apply a translate matrix and move some way, or rotate or scale appropriately. Okay, so once we've done that, all of our vertices are now defined relative to the origin of the world, because we've moved our model transform matrix. Okay, so if I have this figure here, maybe it's local coordinates were over here where we just sort of said to position it, but we're now relative to the world at the origin here. Okay. Now the next thing is then we have something called the view matrix, and again, this is just a way to help us think about and organize our 3D scenes. The view matrix tells us where our camera is. Okay, so we've moved this model around, and then maybe we are translating our camera backwards, in the sense that we're just applying translation matrices to our view matrix to move around in our scene. Okay, so now all of our vertices are relative to the camera, or where we're viewing our scene from. Okay, so another way to put this is the world is moving around you, if you'd like. And again, this sort of makes sense because a computer doesn't know what's going on in the camera. This is again this idea of, are you moving in the world, or is the world moving around you? It doesn't really matter, but we're just translating a camera back as a separate matrix to view our scene. That's the view space transformation. Okay, and then once we have everything sort of positioned and located relative to our camera, we then want to apply our projection matrix. So that is, we need to figure out how to fit everything viewable from our camera into our screen. Okay, so we have this thing called the view frustum, which clips out geometry that's not visible. There might be other optimizations that take place. This thing called backface culling, which removes stuff that we can't see. Again, the backwards back-facing triangles, if you will. And then when everything's in this space, then you can either you can apply your projection matrix, which we've been doing as a perspective view, or you could do an oblique or orthogonal view. But again, we're doing things realistically with a perspective matrix. Okay, so here's just again a visualization of that. Our scene, so our camera is here, and you can see the view frustum here rendered in red here of just this grid of cubes. So we're expecting to see 3 rows of cubes here. And then when the projection matrix is applied, everything shrunk down into this sort of unit cube here. If you'd like to think about it this way, this is your or at least this face here is the front of your monitor, and you're sort of looking out to the scene this way. Okay, so this is what the scene actually looks like, and this is what you see in your camera here. It's a little bit hard to visualize, but you can sort of see where the intersections are on these two shapes here. Okay, so that's what your camera actually sees, and you'll also notice the coordinates in this clip space are from typically -1 to 1, -1 to 1. So stuff is centered at sort of 0, 0 when you're drawing your triangle or whatever. Okay, and then there's one final transformation to move us into screen coordinates. Again, this is the GL viewport command, but it's taking something like -1, 1 here, -1, 1, or whatever these dimensions have to mean, and moving them into, typically what you think of in your window or this 2D space, just how many pixels there are, what the resolution of your window is. So maybe it's 800 by 600, for example, or 1024 by 760 or whatever. Okay. So again, that's just a little review and reflection on what's going on with the MVP matrix. It can be helpful again to just think of it as this pipeline. Okay, so in our code, what we have so far is relatively static scenes. We haven't really done anything with our camera, our sort of viewing matrix. Okay, we can move the objects around and reposition them, but now we actually want to move around in our world. Okay, so now we need to figure out how do we modify this view matrix, and what are the components of it, of how we view our scenes. Okay, and again, keep in mind when we have the view matrix, the way we are actually doing things is we are moving the world around the camera when we have this setup here. We're translating our camera or our world backwards and sort of keeping our camera stationary, if that makes sense, because we're applying our view matrix after moving our stuff. Okay, so here is the actual camera class, which I want to introduce to you folks. And it's made up of 3 vectors. That's what your camera is. Okay, so you have the eye position. Again, you can just think of this as yourself. If you're looking at the monitor itself, it's where your eyes are, their location here. So where is our camera positioned? Eye position. The view direction, that is where you're looking. So if you turn your head to the left, your view direction has changed. If you turn your head to the right, it's changed. Same thing with the camera. And then the up vector, okay, which tells us where is up in our world. Okay, so this is our camera setup here. Okay, so the eye position is where the camera again sits in the world space. So moving our eye position, or this vector that has x, y, and z, is what's going to actually move the camera around in our scenes. Okay, so there's going to be a few member functions for you to implement today. moving forward, moving backward, moving left, right, up and down. And again, these are very positional attributes of our camera. So that means they have to do with the eye positioning. So where you're actually moving. This is your legs carrying your head with your eyes and moving you around in the world here. The up vector, again, tells us where the up direction is. So this is something that you can set up in your camera constructor. Typically, again, this is 0, 1, 0. That is up in the world is, sort of looking up in the sky, straight up along the y-axis. That's typically what we're going to want in our scenes. You might think about manipulating where up is in the world if you're doing a space simulator, or want to sort of model this after the sail of a boat and sort of have a tilting or rocking back and forth of the camera, which can be kind of a neat effect. But for now, it just has to be up for us. And then finally, for the view direction, you're going to have to think about where that is. But we're going to, with our view matrix, think about how to use our mouse to control where we're looking. Okay, so if we move our mouse to the left, we're going to look left. If we move our mouse to the right, we're going to look right. So there's a few, there's one helper member variable here, the old mouse position, that's going to keep track of where our mouse is, or excuse me, where our mouse was, and then our current position is sort of where we're going. And that sort of gives us a direction. It gives us a starting position, ending position to tell us that we moved, X units left and Y units up. Okay, so the mouse look function will be where you work with the view direction. Okay, so again, the view direction is the vector. It tells us which direction we're looking in. Usually, down the z-axis. In our previous labs, we were just looking straight down there, but now we can actually, we're going to work on implementing this mouse look function so we can look around at our scenes. Okay, and we need two vectors to give us a new vector. That's why we're going to record our old mouse position and have our current mouse position as well. Okay. So some GLM related things that you're going to see in the starter code today is you're going to have a bunch more objects. So they're all in this array. And each of these objects model space matrix is again in transform.h if you want to see what that is. Get transform returns that model view matrix. Okay. We'll want to also keep in mind that GLM works in radians if you're going to do any sort of rotations. So you'll notice there's a little scene set up with a wall. I can go back to where what we're going to be doing today. So there's this sort of brick wall, and there's actually different walls facing different directions here. I've rotated those each 90 degrees in one direction or the other, and you have to do that in radians in GLM. Okay, so that's the function that converts an angle to radians. The system works in radians. Okay, so building the camera, just a note on this, and there's a note in the lab as well, that the camera class is implemented as something known as a singleton. Okay, so some of you who might have taken the software engineering course already might have seen some of these different design patterns, and for others this might be new. The good news is it's a kind of cool design pattern that has uses and reasons not to use it, but it basically means our camera becomes globally accessible, and we only have one camera total in our scene ever. So we can only instantiate this camera one time. Okay, so anywhere that you do include camera.h, you get access to the camera. Okay, and you're going to use your camera by doing camera. Here's the scope operators, and then you can call a function on your camera. You'll read a little bit more about how this is possible with static in your lab, but then you just call a function move up, and it will move your scene up or down once you've implemented everything. Okay, so for building the camera, we have get world to view matrix, and you're going to see that per object, you'll build the MVP matrix, and then that's what eventually gets sent into each of the object shaders. Yes, it's a little bit wasteful, but we'll add some, more abstractions later to sort of clear that up. Okay, and then once you've done this, the MVP matrix is applied to each of the objects with the same camera and updated accordingly. Okay, and then note or remember from your previous lab where we implemented the MVP transformations on the order of how we want to create this MVP matrix here. So it's MVP backwards, so we get our mono view matrix, our view matrix here. This is from our camera, we'll get its view matrix, and then the projection matrix. So M here, V, and P. Okay, and then you're sending into that particular object's shader a uniform with the MVP matrix. Okay, and this is a 4x4 matrix. Okay. And just as one bit that wasn't covered here is just the GLM perspective. Again, this is our projection matrix. We're doing things in perspective. That's how we want to project our 3D scene. So we have the field of view, how wide it is. You can play around with this a little bit. Maybe you remember our star field from long ago. We have the aspect ratio, which is the screen width divided by the screen height. The near plane, that's how close can we see things, sort of our blind spot towards our eyes. So stuff closer than 0.1 we will not see, and stuff further away than 20 units in OpenGL we will also not see. Okay, you can extend this to be bigger if you want to see stuff further away, or make it shorter and stuff will get clipped away. Okay, so the goals for the camera portion of the lab are going to be to set up some controls in the SDL graphics program. In the loop function where you handle events, you'll be looking at the mouse and how to use the mouse. You'll be implementing a camera, those functions move up, move down, and the mouse look, and so on. And I want you to have the ability to implement mouse look on the y-axis. That is, if I move the mouse up, you can look up, and if you move it left and right, you also have that functionality. If you want, you can add more controls to your camera, things like jumping, maybe hitting the space bar or something to move your camera up for a second and then let it come down. That could be fun if you get that early. Okay, just a quick aside on OpenGL instancing. I created this little world in our graphics program, and I just want to make a quick note that I'm doing something that's an example of instancing. That is, all of these brick objects here, if you look at the code, there's been another little abstraction added on geometry. I'm just making a triangle out of the same vertex data that we've been pretty much using up until this whole semester on just how to render a quad. So I am using the same geometry over and over again, creating the same buffer or whatever, and I'm just rotating it and redrawing the same stuff. So this is just a sort of aside on instancing. It's a way to more efficiently draw graphics programs. Okay. So there's other ways to do this with only a single GL draw elements call, but you can read more about it here. There's actually a nice tutorial, especially for folks thinking about doing particle systems, where you wouldn't want to create lots of vertices for each of these individual dots here. You're just reusing the same thing over and over and over again. Okay. Okay. So that's just a brief aside. Don't worry about that if that's sort of gone over our heads. Okay, so go ahead and give yourself a little break if you need, and then we'll continue on to discussions about lighting. All right, so if you're joining us back from your break, let's talk about lighting and illumination. So before we looked briefly at this idea of what's known as Lambert's cosine law, this idea that the final color is determined by the angle of where your light source is coming in and hitting your surface. Okay, so I briefly mentioned this before. The more direct, again, so the smaller this angle is, that means the light source is coming closer to the normal, so this surface should light up more. Okay. So the illumination, again, color in our world, you've probably heard that objects are not the actual color we see, but rather the light reflected from an object's the colors that humans perceive. But colors in computers, objects in the real world, we're just limited since we have to represent color by data, so we can't represent everything. So in computers, again, we represent everything with these RGB values, just like in our PPM images. But in OpenGL, these range from 0.0 to 1.0. Okay? Again, our PPM images were just 0 to 255, but OpenGL, everything's normalized within this range here. Okay, so 255 would be equivalent to 1.0. So if we want to simulate the real world, we reflect light by multiplying in a light color. Okay, so we accumulate, or we're sort of in a additive model of R value is, the R value is greater if an object's more red. If there's green in an object, the green value is higher. If there's blue in an object, the blue value is higher, and so on. Okay, so here's an example in which we have a white light that we want to create. So, your standard fluorescent light or something in an office. So we'll create a vector and we'll represent R, G, and B values for this light. Okay, and then here's just another toy color, so that we can multiply through. So we can multiply our vectors and get a new color. Okay, so what this is showing is we get our final intensity. So here's our light. Maybe this is the object's color on its surface that it actually is, and by multiplying them through, we get the final color of that surface, this value here. Okay. So today we're going to learn how to implement light in our OpenGL. That is, we need some abstraction to do this. So in the old world, an old OpenGL fixed function pipeline with no shaders, we actually just had 8 sort of hardware lights that could be enabled or disabled based off of if we needed them or where they were in the world. So actually looking at how this is done is going to be pretty much the same for what we're going to do, except we're doing it in our programmable pipeline. So that means that we get to write the lights ourselves, and we can do some cooler tricks, and we're not limited to just having 8 lights in our world. So if you can imagine in graphics before, they had to represent everything with just 8 lights in a room or in an entire world. Okay, so how are we going to add lights in our code? And this is going to be the first task that you try on your own. So in each object, object update function, you'll see a new uniform representing the red light with a value of 1.0, 0.0, and 0.0. Okay, so here is in your shader, you're going to create some uniform here. Again, this name light color is going to match exactly what's in the shader, and then the 3 values. You're sending in 3 floats here to that shader. And then in our fragment shader, of course, here's the corresponding light color here. And by putting in a red light in our scene, that means our objects are only reflecting back red, or the red values. Your initial brick wall scene like this will now look red like this. Okay. So you're multiplying in for each fragment, each tiny pixel on this texture. It's diffuse color, so this is a brick, so kind of a reddish brown color, by the light color to get the final color. And then the last value here, RGB, this is the alpha value, so RGBA, so it's fully opaque, we can see it, no transparency. Okay, so by having a red light in our scene, or telling our shader, hey, there's only red light in our scene, we've essentially just zeroed out all the blue and green light that can be reflected back in our scene. Okay, so that's how we've represented color. Okay, so introduction to lighting. Again, in order to set up lights in our graphic scenes, we want to sort of simulate how things work in the real world. And as you can imagine, or I'm just going to tell you, this gets really computationally expensive, trying to simulate how light bounces around in the world infinitely many times. Okay, and in our computer we can't have a you know, a light ray that bounces around infinite times, that's going to take forever to simulate. And if we have, you know, thousands and thousands of different colors and so on, you know, so we need to come up with some way to sort of fake a realistic looking light. Okay, and the way that this has been done that's worked pretty well is something called the Phong lighting model. Okay, so let me introduce to you this lighting model. There are three main components of light and how we talk about light and how surfaces are lit that can make them look relatively realistic. Okay, so there is the ambient lighting. This is the overall lighting of a graphical scene. If you want, you can think of this again like the sun. If it's a cloudy day like it is today currently for me, or it's outside raining, you know, there's not a lot of brightness outside. But when the sun comes out, you know, it's a fully sunny day, things are brighter. Okay, and that's the ambient light. You can sort of think of it like a dial on how bright your scene is for that particular color. Okay. The second component is diffuse lighting. That's a light that reflects uniformly across a surface from a light source. Okay, so just imagine you have a very matte or, you know, not very reflective surface like a wood desk, and you're shining a light on it, you know, your fluorescent office light, and it just sort of scatters across that surface uniformly. Okay, so it's all like a woody texture or something. Okay, and then specular, the third component, is the bright highlights on a glossy surface. Okay, that's these sort of you know, bright reflective surfaces that you see here. Okay, these are, you know, a way to sort of you know, if you've ever taken a photo with a mirror in the background, or, you know, some highly reflective surface, you'll get these sort of bright spots. That's a specular highlight. And that's basically means the light path, so where you're taking that photograph from, is reflecting exactly back at the camera. Okay, that's why you don't typically take pictures against reflective surfaces like against a window or something, or a mirror, because then you get that bright pattern here. Okay. So here's another view of it just with a color image, since we're talking about color and lighting. But here's your ambient lighting, so just how light or dark the scene is of this orange box. So maybe it's a cloudy day here. And then the diffuse component, again, is just the color that's going to be distributed equally across this surface, right? So this whole side of the cube here, this whole face, this whole quadrilateral here, is lit the same color. Versus, you know, to the side here, this is, you know, it's less bright, but it's uniformly the same color. Okay, and then the specular component here, that's this sort of bright spot here, is, you know, where your light source is really coming from. So you can see it's directly, you know, this bright and sort of glossy looking surface here. Okay, and then when you combine all of these components, your ambient plus your diffuse plus your specular, you get this final image here. Okay, so you get this mostly orange or brownish face here, and then the bright spot here, and then, you know, this side is lighter, and so on. Okay, so again, in our Phong lighting model, three components: ambient, diffuse, and specular. The ambient component, again, is just that there's, you know, almost always some lighting source in the scene, the sun, the moon, whatever. Diffuse component brightens up faces that face the light source uniformly here. And then specular is the bright spot that reflects back the color of the light. Okay, so the full Phong illumination model, if you'd like to see it just for the math minded, is here. And we can take a very brief look at it. And, you know, these equations can be a little bit intimidating to look at, but let me break down the components a little bit for you. So what we're solving for is on the left side here. This is the intensity of the light. Okay, so how bright is something going to be? How orange is it going to be, you know, in this scene here? The A part is the ambient component. Again, so ambient is just sort of like the sun, you know, how much of the clouds are covering it, you know, just like a little dial or a dimmer switch. if you will, and how bright your scene's going to be. This summation here is for all of the lights, so you might have multiple lights coming in. And then we have the diffuse component here, and then the specular component here. Okay. The diffuse color is based off of the normal dotted with the light source, the direction the light's coming from. And if it's very direct and head-on, then it'll be brighter. If it's not very direct, it's totally parallel, then you'll have no diffuse component here. Okay, so this is back to sort of Lambert's law. Okay, and the same idea for specular. This tends to be an exponential function. That's what this a is over here. Y is exponential. Well, where the light is directly pointing, this midpoint is very bright, and then it exponentially decreases as you go further away from where the light is pointing here. Okay, so you can make it sort of very quickly darken or reduce the specular component by making it an exponent, and then you just have some constant factor here. Okay, and then this is the same equation, but just broken down, showing you do this for the R, the G, and the B. Okay, so if you want, you can take a little bit more look at that, but that's what's going on for folks who want to dig a little bit deeper here. Okay, so ambient, diffuse, and specular. Ambient, again, is just added. Diffuse and specular are the dot products, again, and so on. Okay, so the Phong lighting model, ambient light, get an order to compute or build this Phong lighting model. We need some intensity value. Okay, so what we're going to do, this is part of your task 2 of your lab, is create an ambient light. Okay, so in your shaders, you're going to create an ambient intensity. This is just some fixed value. It could be this 2. You can play around with it, make it 200, and see what happens to your scene. But this is how you'll communicate back and forth with your shader. Okay. So here's with a value of 2, I have effectively brightened everything to be twice as bright. Okay. So here's a very bright, I'll call sun, to our scene. Okay. Again, ambient light, you can sort of just think of as the global, light that's available, something that's globally available. Here's just another image of cool lighting stuff, sort of interjected here, again, to think about your final projects. Okay, back to the Phong lighting model. Diffuse lighting here. Okay, so again, diffuse lighting is, again, what's going to start making our scenes look more and more realistic, in that it's a cheap model to have, that we just say, hey, light up this particular triangle uniformly, but not all triangles. If you've got let me show another illustration here. This face here, or these triangles, aren't going to be lit up in the same way that these ones are. Okay, so it gives us sort of that nice effect to create more realism in our scenes. Okay, so again, this is just depending on the angle or the dot product, really the normal of a face and the direction of the light. Okay, it's just that dot product. Okay, so it means that the dot products is 1 if the angle between the normal and the light vector is 0. So if I move that light directly over here, we would have 1 here. That would be a very bright diffuse lighting here. Then if it's totally the direction that the light's going is totally parallel to this surface, then the dot product is 0, so we would not see much diffuse light. Okay, so here's just another rendering of what's going on with diffuse lighting. Again, regardless of where the light source is hitting, the light scatters equally across this surface. That's why there's all these equidistant arrows here. Okay, so to implement diffuse lighting, here's what we're going to do. So we'll need a few tools to help us out here. We'll need at least 2. We'll need the normal vector that's perpendicular to our triangle surface. So this time we're actually going to have to compute and make use of these normals. I know folks have been asking me in office art, when are we going to make use of the normals? Well, now we need to. And in this case, in geometry.cpp, you'll notice that I've already given you a default orientation for the normals, okay, the direction at which the light's going to hit the surface. Okay, so those are already going to be set up in your triangles for you. Okay. Okay, so we need to then pass in the information in our vertex buffer objects. So that means we need another layout for it. So we're going to create buffer normal map layout, which is going to actually set up the normals in our scene. Okay, so this means again we're going to pass in information about our position of our vertex, the normals, the texture coordinates, and I'm going to jump ahead a little bit because this will help you for your next assignment. I'm going to add in the tangent vector and something called the bitangent. We will talk more about that soon, but just know you've got starter code set up for you in this lab, so you don't have to really do anything with the tangent or bitangent right now. Okay. So those are the two things. We needed to compute our normals and then actually pass them through by creating a new buffer layout with that normal information. Okay, so task 3, we need to compute diffuse lighting. Okay, so now that we know we have our normal data in our vertex shader, we've just passed in the normal information for each and every one of those triangles. Again, in our vertex buffer object, we got to pass this information to our fragment shader. So you're going to see there's a little out vector 3, my normal, that's passed from, this is your vertex shader into your fragment shader, which has the little in thing, so for your graphics pipeline again. And again, this will be useful for assignment 5. And then additionally, we need to output the fragment position. And this is, I wrote a little bit on the lab, and this might be a little bit of a weird thing, but from our actual vertex shader, we need to output the fragment positions as well. And this is because we might have rotated a object in some way, so we need to send that information to our fragment shader to say, hey, this shape is actually rotated at 90 degrees, so we want to make sure all the normals are pointing in the right direction for that. Okay, and I'll let you think about that a little bit, but again, the idea is if I have this scene here, this brick wall, which has normals that have been generated for it, pointing, say towards the screen, and then I create another brick wall and it's pointing now, the normals should be pointing this way. We want to make sure that the fragments, each of these little fragments have their normals pointed this direction as well, to the left. Okay. Okay. So then our fragment shader is going to import, again, our normal and fragment position data. That's what's coming in here. And additionally, a light color and the position of our light, because we need to know where that light is relative to our actual geometry, and then the light color, which is how we're going to color our scene. Okay, and all of this information, all these uniforms are going to be passed in the object update function. Okay, so now the final steps are going to be to compute the diffuse light. We'll need to normalize our normal, that is to make sure everything's between the value of 0 and 1.0. Then we need to figure out which direction the light's coming from. So we need to create a vector. Okay, so we have our light position, where our light is in the world, and then our fragment position, okay, where our fragment is in the world. Right? We've imported some geometry and then rotated it in some way, and now I have a new position here. So subtraction of two vectors gives us a new direction, and we call this the light direction. And then we can take the dot product of this newly computed light direction with our normal of our object, and that's going to tell us, based on that angle, some range -1 to 1, how much to light up our image. Again, so if it's directly pointing, if the light's directly facing our object, 1. If it's totally behind our surface, -1. If it's totally parallel, 0 with our image. Okay, And the final step then, once we've computed this, is to multiply through the diffuse color by the ambient intensity. Okay, so here is the full main code in our shader. Again, the stuff above this in our fragment shader is setting up stuff, but again, here's our diffuse color, which we get from our texture. We compute the ambient light, which is just what's the color of our light times the intensity. Then we compute our diffuse light. So here it is in code, this sort of written explanation. But you have a normal, you're normalizing your normals just to make sure they're within a valid range, 0 to 1. Computing the light direction by subtracting the light position minus the fragment position, and then normalizing that value. Normalize is a built-in GLSL function, so we don't have to, so that's where that comes from. And then we compute the diffuse light impact by taking the dot product here of our normal and the light direction. So our normal is, again, where our normals are coming from, and the light direction that we just figured out, where's the light coming from relative to my fragment. We don't want this less than 0, so here's another handy max function here. And then we compute the diffuse light by saying, hey, what's the impact of the light? What's that, going back to our Lambert shading strategy of saying how much of that light's facing a surface, and then times our light color. And then we put it all together. We have our lighting equals to diffuse light plus our ambient light. Okay? Okay, so then we get something like this. So you can see, on the right side, it's a little bit subtly different, but you can see it on the grass or on the brick wall, especially if you look towards the top. It's a little bit more lit up, if you will. Okay? So it's a little bit, it's still a little bit of a boring scene though, so we need to add the one more component left with our Phong illumination model. And that is, well, we've computed the diffuse lighting again, but now we need to compute the specular component. Okay, so this is the grand finale for our, to add to the diffuse lighting, again, is to have the specular component. Okay, so this is again the light angle that hits a surface. Okay, so here's our light. Here's where we're viewing our object from. Here's our normal. Here is the angle that the that is reflected from our light source. So it's sort of it's reflected across the normal vector here. So here's our light. It comes in, comes in, comes in. Here's our normal, and then it's reflected or bounces on the sort of same angle away, but in the opposite direction across our normal. So we call this reflect. There's an actual function for that. And then this is how we compute the specular component from this reflected angle versus when we're viewing. Okay? Okay, so light again is strongest based on where the light would hit the surface. Again, imagine shining that flashlight against some surface and at different angles. And we need this reflection vector here. Okay, so we got a handy GLSL function to do that for us. Okay, so if this angle is tiny and approaches 1, the specular light increases. So here are some examples of the reflection vector being created around the normal, and then different constant values, or how intense we want to make the specular lighting. We call this the specular strength. So 2 is pretty low, 256 is pretty high, so you can see it's much more intense and sort of brightens up here. And more intensely focuses that light, however. It's a little bit more dispersed with a lower specular strength value. Okay, so how we compute our specular lighting. We first start by sending the view position again into our fragment shader, because we need to know where are we viewing this scene from, right? This is our eyes. And then next we compute the view direction and the reflection vector. Okay, so here's our view. We just sent that in and set up the specular strength, whatever constant value we want. And then we need to compute the reflection direction. Okay, so here's where we're viewing from. The view position. Here's the view direction. So view position minus the fragment position, and then the reflection direction. Okay, we just reflect across that. Okay, and we negate it, the light direction, because again, just light's coming in here, and the reflection needs to happen in the opposite direction. Okay, that's why this light direction is negated. Okay, so now that we know, again, what the reflection direction is, we can take the dot product, again, to figure out how strong is our specular light. That's sort of the theme here. So here's our spec. And we take the dot product here where we're viewing from and where the reflection occurred. We have some exponent of how fast this is sort of going to decay. And then we compute our specular lighting by multiplying the strength times, well, what we just computed here, times our light color, okay? And then after that same pattern, we just do the same thing. We add to our light model. So here's lighting. Again, it's an accumulation of lights of the diffuse, ambient, and specular component. Okay, and once we've done this, if you look towards the center of the scene, you can see that it's a little bit brighter here, and then it disperses and gets lighter. So this is our original with no lighting, and here's our scene with the diffuse, specular, and ambient light applied. Okay, wow, so that's a lot. It's a lot of talking, a lot of looking. It can be helpful to look at the code here, but so a version of the shader is provided for you. You're welcome to do something else if you like, but I've provided most of the shaders for you today. Just because it's helpful to actually read through the comments and try to play around with the code for this lab. Okay. So some notes, again, since you can sort of play around with the shaders, remember that since you're working the shaders, those are always recompiled when you're running your code. So that means you do not have to recompile your C++ every time you change something in the shader. You just have to rerun your executable. You only have to recompile your programs when you change something in a C++ or a .h file. I did want to mention that there's different kinds of shading models. Of course, there's the Phong illumination model, but there's also the Gouraud shading model, and this one it gives us a sort of more performant lighting model, but it doesn't look as good. You'll notice the Phong illumination model is much more sharp as opposed to this one. Okay, so just know that there's two, but they work on the same principles. This one works on a sort of per fragment basis. You get a normal, and this one, right, we had those little frag positions. This works on a just vertex normal, so that's why you get sort of these ridges and it's not as sharp. Okay, there's just a few other lighting notes. This lighting process that we did sometimes is considered expensive, right? We're doing it in real time, but our GPUs are fast, but you add enough lights and enough cool effects, which we'll be doing soon, and it can slow things down. So some people actually go through the effort of pre-calculating the light, and this is something called a light map. So here's a sort of tunnel, and then they sort of simulate in a 3D program where lights would be placed and what this would look like. This gives a pretty cool effect, and then it's just you just put this texture to the object. The disadvantage, though, is that the light is sort of baked into the scene, and you can't have a dynamic light. So if a character is walking through here with a flashlight, it would look the same regardless, or if it's day or night. So that's why we try to do the lights dynamically, and we can't. It's more real. But this can be a pretty good compromise, pre-computing the lighting. Again, this is just the different light sources. We've talked about an ambient light, and we've talked about a directional light. Assuming we have a light in our scene that sort of goes on forever. But there are other kinds of lights. There's something like a point light. There's area lights, emissive lights. Again, you can think of like neon scenes here, flashlights, lightning bugs for emissive things. Area lights could be like a very focused, like a light under a microscope or something. A point light could be like when you're driving on the highway, a spotlight of sorts. So there's many different other light sources that you can abstract upon. We've sort of just had this directional light today. Okay. If you've got extra time, a cool tutorial to try is the Learn OpenGL tutorial on implementing something called a light map. I've included some of the PPMs in the repo if you just want to play around with these, but the basic idea is you can have a texture here and then a separate texture, a second texture, where the specular component is encoded as a sort of grayscale image. So black means there's no specular highlights, gray or white means it's highly reflective, and then it can give you sort of this nice specular, you can see in the corner of this cube here in this image on the right, highlights. So that's just something you can look at for a bonus. The lighting stuff gets pretty cool, so feel free to take a look at that. Okay, so your goals for task 2 is to implement the diffuse lighting model. Again, the shaders have been set up for you, but you get to play with it a little bit. So implement those, type them out, make some mistakes, try some things, and then peruse your code to make sure your normals, your uniforms are correctly sent in. Okay, and just a little bit more if you want to hear it from somebody else on diffuse lighting. Okay, so here's your lab goals. The lab's been pushed to your repo, so you obviously may begin, and we will see you during office hours and so on. And don't forget to do your in-class activities. All right, that's it for today. It's a big one, so you can think about your final projects, knock out this lab, and we'll see you next time.